Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. In the previous two videos in this playlist, we looked at the notion of performing line integrals and surface integrals on an arbitrary manifold. In this video, I want to look at the general notion of integration on manifolds, and here we'll look at high dimensional forms or differential forms. To start with, we need to look at the theory of multilinear algebra, and that involves K-forms on vector spaces. Okay, so let's start with some finite dimensional vector space V over the reals, although you can do this over other fields as well. And suppose it has dimension n, so we can pick a basis, say B1 up to Bn. We'll also need to consider its dual vector space, okay, V star, which just is the vector space of linear maps from V to the ground field R. This is also n-dimensional, and in fact there's associated to this a canonical basis called the dual basis, B1 star up to Bn star. So B1 star will have the value 0 on all basis elements except for the first one, B1, and it has the value 1 here. And similarly for the other dual basis elements. Okay, so we can now define something called a K-form on this vector space V. And the definition of this is motivated by what we saw in the definition of a 2 form when we were studying surface integrals. Okay, so here, this K-form on V is a function from V to the K, so it takes inputs, which are K tuples of vectors inside V, and it spits out some real number. And this function has to satisfy two properties, okay? So the first one, and this is something that we saw in the notion of a 2 form, is it should be linear in each of the variables V1 up to Vk. That's the first property. The other property is that suppose instead of evaluating this at V1 up to Vk, we evaluate, so here we go from V1 up to Vi minus 1, but instead of having Vi here, we put in Vi plus 1, and then we have Vi, and then the rest are as normal. In other words, we just switch the Vi and the Vi plus 1, then the value of L is the negative of L of V1 up to Vk. Okay, so that tells you if you switch two consecutive variables, the value should negate. Now, of course, the whole permutation group on n symbols, the symmetric group on n symbols, acts on these variables. And that symmetric group is generated by these transpositions of consecutive terms. So in fact, what this shows you is if you swap any two variables, then the value of L negates. And more generally, if you permute these variables via some permutation, the value of L will change by the sign of that permutation. Okay? So a K-form on V is just some function, L, from Vk to R, which satisfies these two properties. Okay, so we can look at the set of all these functions, okay, and we'll call that wedge K V star. And it's actually a vector space, okay, so how is it a vector space? Well, here we're looking at functions from some set to R, so the set of all functions from this set to R forms a vector space under pointwise addition and scalar multiplication. So you can ask, are the set of functions which satisfy these two extra properties, is that closed under addition and closed under scalar multiplication? And what you'll find is that's the case, and in fact this does actually form a subspace, so hence this is actually a vector space, so we can talk about its dimension and things like that. Okay, so let's try to get a feel for these two conditions by just looking at a simple example. Okay, so we'll have here L is some element of wedge 3 V star, so it's going to be a 3 form on the vector space V. And let's suppose we evaluate it at something like VVW, so an instance where the first and second vectors are the same. So these vectors are all inside V. Okay, so now if you swap these two vectors, which doesn't do anything, then the value of L has to negate. So L of this is equal to the negative of the L of this. So in other words, this is some real number which is equal to its negative, and since we're working in characteristic 0, that means that this real number, L of V, W, is equal to 0. Okay, so that's rather interesting. Okay, just from this property here, Okay, we see straight away that the value of L here has to be 0. Okay, and what can we sort of see happens more generally? More generally, if you have any two of these vectors, input vectors are the same for a k-form, then the value has to be 0. Okay, so I hope that shows you a little bit of what you can conclude from this axiom B. Okay, so let's have a look at the linearity in each variable, and that's often called multilinearity. And that's why this forms part of the subject of multilinear algebra. Okay, so we'll just do a simple example like this one here. Let's suppose we evaluate L at this triple of vectors. Okay, and the triple is given by the first vector is 3v plus w. So here u, v, w, and x are just some vectors inside our vector space V. So it's L of 3v plus w, comma u plus v, comma x. Now it's linear in each of these variables. Okay, so it's linear in particular in this first variable. So we can break it up according to the linearity property here. So we fix the u plus v and the x. Here's the u plus vx here. And we break it up to 3L of v, and there's the u plus vx. And then the L of w, and then you have the u plus vx. L of w, u plus vx, like that. Okay, so that's rather nice that you can, once you know the values of L on these simpler looking vectors, you know the value of L here. Okay, we can go further because we've also got a sum in this term here. Okay, so this one here, you can use linearity in the second variable now to expand this out. Okay, so this is now 3L of v ux, that's this term here. And you've also got 3L of v vx, that's this term here. And then you can similarly expand out the last one. So you have LWUX here and LWVX, which is here. And if you look closely, actually, there's some further simplification because the v here gets repeated. Okay, and as we saw, if you have a repeated vector for the inputs, then that is 0. So in fact, when you expand this out, you get 3 terms, not 4. Okay, so I hope that gives you a bit of a feel for what these multilinearity and this condition here is called the alternating condition. So sometimes these are called alternating k-forms. Okay, so what does this show you more generally? Okay, so if you want to evaluate L of v1 up to vk, using linearity in each variable, we see that the possibilities are limited depending on what they are on basis vectors. Okay, so for each v1 up to vk, we can write it out as a linear combination of basis vectors b1 up to bn. So once you've done that, of course, you can expand by using linearity in each variable, okay, much as we did over here. So we broke it up into the individual constituent components, okay. So this function L is just completely determined by the values it takes on bi1 up to bik, where these are just some of the basis vectors. But more is true, because often these might be 0. If 2 of them are the same, then it's going to be 0. Okay, so we don't need to consider any of these k-tuples of vectors if 2 of them are the same. And in fact, also, we can arrange them by this property here, right? If you permute them by some permutation, then the value of L will change in a set way depending on the sign of that permutation. So we can also always arrange it so that these basis vectors are such that if you look at the corresponding indices, I1 up to ik, they're in strictly ascending order. So in other words, we just need to look at the value of L on bi1 up to bik, where what are the possibilities for I1 up to ik? Of course, they're in the range 1 up to n, but we can assume I1 is strictly less than I2, is strictly less than all the way up to ik like that. Okay? So the other thing is that, well, okay, that means that it's completely determined by these values. How many of these values do you need to specify this L? Okay, how many is that? Well, you just need to pick these k indices from this n choices. So that's n choose k. And that tells you straight away that the dimension of this vector space, wedge k v star, is at most n choose k. And we'll see in a short while that actually you have equality here. So that gives you a good feel for what this vector space of k-forms on V is. Okay, so let's have a look at some examples of k-forms on a vector space. And we can use the same idea that we used when we looked at two forms. Okay, so suppose instead we have k elements of V star. By the way, these elements of V star, they're the same as just one forms, because for a one form you just need a linear map from V to R, and there is no alternating condition in that case because it holds vacuous. Okay, so suppose you have one forms L1 up to LK. In that case you can form a K form from those K1 forms, and we'll call it L1 wedge, L2 wedge, all the way up to LK. So what is this? So it's something where you input a K tuple of vectors from V, and it has to output some number, and this is the number that I want to output. So what I basically do now is I'm going to form a K by K matrix here. Okay, so in the ith row, I'm going to take the ith member here, so Li, and I'm going to apply it to each of these V1 up to Vk in turn. And that will give me the ith row, and I can go through all the K rows like that to get some K by K matrix here. And since it's a K by K matrix, I can look at the determinant of that. And I claim that that is actually a K form on V. And to check that, it's quite easy actually. So for example, what do you want to do? Let's see what happens if we swap two consecutive vectors here. Okay, if we swap two consecutive vectors, over here we just swap two consecutive columns of this matrix, and hence the determinant negates. That's the alternating condition. What about linearity in each variable? Let's check that too, and it's quite easy. So suppose we look at the jth vector here, so Vj, and we scale it by some scalar. Okay, if we scale that vector by some scalar, what happens here? Well, Vj corresponds to the jth column, and these are all linear functionals on V. So that means that this jth column gets scaled by that same scalar as well, and hence this whole determinant gets scaled by that amount. And similarly, you can show that this function preserves the addition in the jth vector. Okay, so it is actually linear in each variable. Okay, so that's great. That gives us lots and lots of examples of K forms. And once we have them, of course, you can take sums of things like that as well. Okay, so let's look at some very simple examples of this. So let's go back and assume we have a basis of V from B1 up to Bn. And so we also have a dual basis, and we can consider elements of the dual basis Bi1 star up to Bik star and form their wedge like that. And let's suppose that these I1 up to Ik are increasing order. Okay, so to work out what this is, remember, you just need to evaluate it on K tuples of basis vectors of the following form: Bj1 up to Bjk, where J1 up to Jk are in strictly increasing order. Okay, so let's see what all those values are. Okay, well, it's quite easy to see that if you have these J1 up to Jk the same as I1 up to Ik, since this is a dual basis element to these ones here, then actually the matrix that you'll get here is just the identity, and the determinant of identity is just 1. Okay, but as soon as they're different, okay, so once these two increasing sequences are different, then they have to have a different element. And I claim that then you get 0 as the answer. Okay, so in other words, this will either be 1 or 0. It's going to be 1 if this sequence is the same as this sequence here, and it's going to be 0 otherwise. So in other words, it's the product of this set of Kronecker deltas. So delta I1 J1, which means that I1 and J1 have to be the same to be 1, and times delta I2 J2, and so forth down to delta Ik Jk. Okay, so let's see why that's true. Okay, suppose it's different. Okay, and so one of these doesn't occur here. Okay, one of the indices here doesn't occur here. Okay, for simplicity, let's suppose that that's that I1. Bi1 doesn't occur as one of the J's. So that means that when you evaluate Bi1 star, so that corresponds to some row in this matrix, on each of these basis vectors, since this is a dual basis element, you'll get always 0. So you have an entire 0 row in this K by K matrix, and hence the determinant is 0. Okay, so that's rather nice. Okay, but what is the interesting that you see from this calculation? So we see lots of examples of, firstly, K forms which are non-zero. Okay, they're not always 0. Then you can find such a K tuple for which the value is not 0. But in fact, it's easy to see that these are all linearly independent as well. So since they're linearly independent, we know the dimension has to be at least a number of these, and how many of these are there? Well, you just look at the number of these increasing sequences, I1 up to ik, and of course there are n choose k of them. So we saw before that the dimension of this wedge kv star as a vector space was at most n choose k, and now we find this many linearly independent elements inside this vector space, so in fact we have equality here. Okay, so that gives us a real good feel for what this is, and in fact it gives us actually a basis for what this vector space is. So let's look at a very special case of what happens when you pick this k to be the highest possible. So for starters, we see that if k is more than n, of course, then this is going to be zero dimensional, in fact, okay? And that's basically because you can always put basis vectors here, and if you have more than n variables, then of course you have to have a repetition of the variable, so you get 0, okay? So this only makes sense for k between 0 and n, and let's pick the highest value for which it's interesting, so that's n, k equals n. So we're looking at wedge nv star. In that case, n choose n is 1, and so this vector space is one-dimensional. It's one-dimensional, and we can also give you a basis element. The basis element is what we put in here, some increasing sequence of n indices. So of course that's just b1 star up to bn star. So it's actually spanned by b1 star wedge up to bn star. Okay, so any element inside here, if you pick any L inside here, it has to be a scalar multiple of this. And in fact, it's very easy to say which scalar multiple of it actually is, okay? If you want to say what scalar multiple is this L of this one here, well, just remember, if you evaluate this at the n tuple, b1 up to bn, you get 1. So to say what multiple of this you have is you just evaluate this L at the basis b1 up to bn and see what number that is. And that's the scalar multiple of this that you need. Okay, that gives you back the L. Okay, so that's rather nice, and that's a very important special case. Okay, so let's specialize a bit more to this V being just Rn. Okay, so that's just the usual vector space you first study. So if you look at wedge n Rn star, and you can do the same thing. So here's our basis for this wedge nv star. And it depends on the basis that you give here. So we can pick the standard basis for Rn and see what happens, okay? If you pick the standard basis for Rn, okay, so let's suppose we input this n tuple of n tuples, so vectors from here, which are n tuples. Okay, so what do we need to do? So in each column, you'll get a Vj. What do? You evaluate using the dual basis. Okay, the dual basis. Okay, so b1 star up to bn star. And what does the evaluating at each of the dual basis elements do? Well, basically it just picks out the coordinates. So the ith basis element will just pick out the ith coordinate. So basically, when you look at the first column of this, all it will do is it will just feed you back that column vector v1. And v2 here, in this expression here, when you have the li's, is now the dual basis vector to the standard basis vector, and these are the basis vectors, you'll just get back v2. So basically you just get the n by n matrix whose columns are just the vectors v1 up to vn. And this basis element that we've given for this thing here is just the function which sends this n tuple to the determinant of this n by n matrix. And hopefully you remember that what is the determinant of this n by n matrix? It has a geometric significance, and that's why it's related to integration. Okay? The geometric significance is as follows. If you have n vectors inside Rn, you can form the n-dimensional parallelepiped, which has sides parallel to v1 up to vn. Okay? So this is the n-dimensional version of the parallelogram. Okay, if you have two vectors inside the plane, you can form the parallelogram with those two sides. And more generally, with n vectors inside Rn, you can form the n-dimensional parallelepiped. And you can ask, what's the volume of that? And of course, it's just given by this determinant here, or rather its absolute value. Okay, so of course, this could be positive or negative. So it's actually the signed volume. And the sign is related to the fact that we need to consider orientation. Okay, so there are two things which tell us a lot about this these n forms and also its relationship with integration. So let's go and see how we actually integrate on a manifold. Okay. So suppose we have a manifold X. So what is a K form? So hopefully from my previous videos on line and surface integrals, it's easy to see what type of thing that must be. Okay. So a K form, it's got to be a function from your manifold X. So for each point of the manifold, we're going to assign to it some omega p. And what is that omega p? It's going to be a K form on the tangent space to X at P. Okay, so it's an element of wedge K T P star X. Okay, so we've got lots of examples of such things. Okay, so the ones we are most interested in are the ones which are smooth. Okay, and when is it smooth? Okay, so it's smooth if firstly we can form K forms of the following form. Okay, so we can look at dx1 wedge all the way up to dxn, much like we did with surface integrals, and we can multiply this by some smooth function f. So here the x1 up to xn are just local coordinates. And if you have something of this form, then it's going to be called a smooth K form. And more generally, anything which is locally of this form is going to be a smooth K form. Okay, so now we come to actually integrating. So we want to say, what is the integral over something of such a K form omega? Okay, so what is that something? I guess we need a K-dimensional submanifold of X. And that K-dimensional submanifold, I guess the easiest case to deal with first is when it's parameterized. So let's suppose we have some smooth map from some domain which we can integrate inside K-dimensional space. Okay, so the K-dimensional space say has variables u1 up to uk. And we have some domain where you can integrate over. And this is smooth mapped into X, and let's suppose that the derivative has full rank there, so that it means that you have some diffeomorphism with some K-dimensional submanifold Y inside X. Okay, so as usual, the way we want to define this is we want to write this out as some sort of integral, the usual standard integral on D. Okay, so that's the way we're going to do it. Okay, so it'll be integral on D of du1 up to duk. Okay, it's parameterized, so there's some sort of orientation that's assumed in here. And what is the function of u that we actually integrate? What's the integrand? It's got to be related to this omega somehow. Okay, so I guess if for each u inside D, okay, you can look at its corresponding element inside this y, which is also inside x. And so that gives you some K form there, this omega of sigma of u. Okay. Also the parameterization itself, okay, gives you tangent vectors at any point you like. So you can look at this sigma du1 all the way up to d sigma duk. Okay, so that's K tuple of tangent vectors wherever you like. So you can evaluate it at this point sigma of u. Okay, so you evaluate this omega at this K tuple of tangent vectors, and that'll be some number. Okay, and that's a number for each u, and so you get some function of u here which you can integrate, and that is the definition of the integral of this K form omega on this submanifold Y. To get a better understanding of differential forms, we need to look at functoriality, which is a very, very important concept in mathematics, and here especially so. Okay, so now we're going to look at the case where we don't have just a single manifold, but we have a map of manifolds, a smooth map, say phi from W to X. Okay, now suppose we have some sort of tangent vector at a point in W, point P in W, so V is inside TP of W. And remember, there are various ways to define this, but one way is that it's given by some sort of trajectory which goes through P. Now you have a smooth map phi here. So of course you can just apply phi to this trajectory, and that gets you something like this maybe. So that's phi of gamma of t. And that gives you a new trajectory which goes through phi of p. And hence it corresponds to another tangent vector. So this is what's called d phi p of v. and it's inside t of phi p of x. Okay. So in other words, you get a map from the tangent space to w at p to the tangent space at x of 5p. And this is in fact a linear map. And this is exactly the type of situation that you see if you have a smooth map between Euclidean spaces. Of course, that derivative is just a linear map between the tangent spaces. Okay, and this generalizes that setup in quite a simple way. If you have a linear map like this, of course, you can dualize it. Okay, so the dual map here is denoted phi p star. So it's a map from this cotangent space on x back to the cotangent space. You pull it back to the cotangent space on w. But we can work more generally. So remember, if you have a family of these over all points, okay, then you get a one form. So we can define actually a pullback map for k forms, and that's what we're going to need. So suppose you have a k form omega, smooth k form omega on x. We're going to pull it back to a smooth k form on w. And how that works is quite simple. Okay, so the pullback is denoted phi upper star of omega. And so what's that supposed to do? It's supposed to send to each k tuple of tangent vectors at p. So this will work for each p. It has to send some sort of a number. Okay, so this is going to be a k form on each tangent space here. Okay, so how does that work? So you have w1 up to wk, they're these tangent vectors inside w. So of course you can apply this linear map d phi to each of them, d phi p in fact, to each of them, and they'll give you tangent vectors over here. And since they're tangent vectors over here, you can now use the omega, which is defined on x, to evaluate this k tuple of tangent vectors, and that's a number. Okay, so that's how we pull back k forms on x to k forms on w. Okay, so let's continue and look at our definition of integration on k-folds and of differential forms in a slightly different way. So the old way was like this, okay? The integral of this k-fold omega on this k-dimensional submanifold y, if you're given some parameterization, that's an isomorphism sigma of d with this y, where d is a domain inside Rk, is given by this formula here. So the way I want to rewrite it is I want to split it up into two things. Okay. So the first thing is that, well, you can ask what happens when sigma is the identity and d equals y. Okay, if sigma is the identity, d equals y. Okay, the types of things that you need to integrate are k-forms. So this is a typical k-form, f of du1 up to wedge up to duk. And you can ask, what is that? Okay, so if you use this definition here, okay, it tells you what it is. So what do you need to do? You need to evaluate what this term is here, okay, for omega equal to this k-form here. Okay, so what do you have here? So sigma here is the identity. So when you work out what this is, d sigma to u1, d sigma to uk, of course you just get the tangent vector d to u1 up to d to uk, which is a dual basis to du1 up to duk at every point. So this is just one. So this whole function here turns out in this particular case, if omega is this k form here, it's just f. Okay, so that's what happens when sigma is the identity. Okay, so this is a bit of a change of notation for the usual integration that you have on Euclidean space. And what I claim now is that you can rewrite this formula in a very nice way using Functoriality. Okay, now instead of looking at d, you want to look at y, which is sigma of d, and you want to evaluate the integral of omega on sigma of d. Well, what you can do is you can pull back this omega from your y back to d. So sigma upper star omega is now something on d. It's a k-form on d. So you can integrate that on d if you have this reduced version of what's happening here. Okay, so that's what I claim is true. And it's quite easy to see why this is actually a restatement of this definition here, assuming this fact here, okay, which is a very small part of this definition in the very special case where sigma is the identity. Okay, so why is that? To see why this is true, I guess this is the left-hand side, so we just have to show that this here is the right-hand side, okay? So basically we want to say that this here we can write as f, where this f du1 wedge up to duk is this thing here. That's what we're going to show, okay? So we just have to show that this sigma upper star of omega is equal to this k form on D. And then putting these together will give us this definition 3, the original definition for integration of k forms. Okay, so why is this equal to that? Okay, so remember when I was talking about the proposition, okay, so we're working now inside what? We're working inside Rk. Okay, so, and we have a k form in k-dimensional vector spaces. Okay, so of course it's spanned by du1 wedge up to duk. That was one of the propositions I gave earlier on. And in fact, it's very easy to say what multiple of du1 wedge up to duk it is. Okay, so I also told you how to do that. What you simply need to do to work out, so this has to be at every point a scalar multiple of this. So in other words, it's a function times this. And to work out at each point what scalar multiple it is, all I need to do is to evaluate at the dual basis. So what's the dual basis to this is d du1. Okay, so the dual basis, okay, so if you have du1 up to duk, the dual basis is just d du1 up to d duk. Okay, d du1 up to d duk. So we just evaluate this there. And how do we evaluate it? Well, we'll go back to the definition here. Okay, so you have d du1 up to d duk, and you apply this definition. So here's our omega that we're pulling back, but we're going to use sigma to pull back. So we apply d sigma here to d du1 up to d duk. We apply d sigma to all of these. And of course, what is d sigma applied to all of these? It's just d sigma du1 all the way up to d sigma duk. And then we just evaluate omega on that. So indeed, we see that when we pull back this omega by sigma, you get this, where this f is just this function here. Okay, so this is a nice reformulation of what goes on using functoriality. So what does functoriality mean? It has a categorical definition, and let me just remind you what this is. It means that it basically preserves composition. Okay, so let's see what happens with the derivative first. If you have two maps now, so there's a phi, and now let's say also a psi, which is smooth from x to some manifold z, then you can look at d of the composite, psi composed with phi. So that will map from a tangent space here to the corresponding tangent space here. And of course you can also do d phi, which maps from the tangent space here to the tangent space here, and then d psi, which maps from the tangent space here to the tangent space here. And of course they're equal. And the way it's defined here, it's pretty clear, because to map tangent spaces, I basically just use those maps to map the trajectories. So if I have a psi as well, then you just have a composite of those three. So those two maps apply to this trajectory to give you the third trajectory. And you can see that this functoriality must hold. And of course, you can dualize this. And if you dualize this one forms, you see that the dual of psi composed with phi is just phi star composed with psi star. And more generally, this works for pulling back k forms as well. And by the same reasoning, okay? If you have phi first and then you apply psi, you can do d of psi composed with phi. And then that splits as a composite of d psi composed with d phi. And that shows you more generally that this equation here holds. To finish off this video, there's one loose end that I'd like to tie up, and that's the independence of the definition of integration with respect to parameterization. Okay, so let's see how that works. We'll start with one parameterization of a k-dimensional submanifold y of x. Okay, so we'll call it sigma as usual, so we'll denote the domain inside Rk as du, and let's use the variables u1 up to uk to keep things straight. And what we can do is we can change these parameters to some parameters, say in t. So now we have some domain dt inside t space, r to the k, with variables t1 up to tk, and let's suppose we have phi as this isomorphism. So we can use this to reparameterize this sigma by just composing. Okay, so firstly we do this phi from dt to tu, and this sigma from du to y. So this composite, sigma composed phi from dt to y gives you a new parameterization. And of course we want to say that it doesn't matter whether you use this one here or this one here, the integrals you get for the integral of some k form omega on y is going to be the same. It's independent of which one you pick. Of course, for that to be true, remember there's this problem with orientation. We need this phi to be orientation preserving. So in other words, the Jacobian of this should always be positive. Okay, so let's see what it means for having independence of the definition. So firstly, if we try to integrate using this one here, okay, what's the definition of the integral on y? What we do is we just pull back the k form rather, omega, to here. So you have sigma upper star omega, and we integrate that over du, which is also phi of dt. If we want to instead use this parameterization, we have to pull this back further all the way over to dt. So this sigma upper star omega, now we have to pull back with phi star. So this is where we use Functoriality here. So if we want to pull back by this composite, it's the same as pulling back first by this sigma upper star and then by the phi upper star. And that gets you a k form on dt and integrating the k form there. So these two things we want to show are the same. And I want to show you how exactly the properties of multilinearity and alternating that we insisted on allow you to prove this fact. Okay, so let's see how that works. So just one quick remark about this is that when we wrote down the definition for the integral, remember on y, it was quite nice. All we did was we said that we just pull back the form and we integrate there. So in general, that's how we like to define things. And this formula is also of a similar form. Okay, we have a k form here, sigma upper star omega. Okay, so we can integrate this on phi of dt. And the other thing we can do, since phi is an isomorphism here, is we can pull back by phi upper star and then do the integral on dt, and they're the same. Okay, so this now becomes a general formula that we can use. Okay, so let's see why that's true. And to see why that's true, we'll see that at the end of the day, we just need to know what's happening on Euclidean spaces, on du and dt. Okay, this sigma upper star omega, we can just call it some k form. Okay, and we can forget that we ever worked on this y. Okay, so this is just a fact about integration on Euclidean spaces. Okay, and let's see what fact that corresponds to. Okay, so we'll rewrite this sigma upper star of omega. You can always rewrite it as f times du1 wedge up to duk, and the reason why is at every point du1 up to duk is going to be a basis vector for the space of k forms on the tangents, on the cotangent space. So, or rather on the tangent space. So that means that you, at every point, you have some multiple of that, and so it's some function times this thing here. So let's pull that back by phi, so that we go to dt in this t space here. So that means that this has to be some function times dt1 wedge up to dtk. And let's work out what this function g is. That's going to be the key. What is this function g? Okay. So what we have to do is we have to pull back this function here. We're going to pull this back. Okay. So the first thing when we pull this back is we pull back this function f. Okay. So that's f composed with phi. That's the natural thing to do there. Okay. And then we also have to pull back this this quantity here. Okay. This k form here. So how do we get that? And we want to say it's some sort of multiple of this k form here. And remember, how do we work out what multiple of this k form it is? Okay, all we have to do is we just have to evaluate it on the k tuple of vectors, which is the dual basis, d dt1 up to d dtk. Okay, so we have phi upper star of this, and we want to evaluate on d dt1 up to d dtk. So that phi upper star, how do we perform the phi upper star? What we do is we apply d phi to those basis vectors, dt1 up to dtk. And then all we need to do is just to evaluate this k form on that. Okay. So that's going to be our function g. Okay, so let's work out what is d phi of all these things. So remember, this phi just sends the t space vectors to the u space vectors. Okay, so it's vectors with coordinates t to vectors coordinates u, okay, by this phi. So one way you can write this is, well, d phi dt1, so that's just using the usual change of variables formula. It's just the sum of all dui dt1, so that's now some actual function, times this tangent vector d dui, and you just sum these for all I. And you do the same thing from t1 up to tk. So these are now tangent vectors. You applied the d phi to these tangent vectors, and now tangent vectors sitting over inside this u space over here. Okay, but at the end of the day, this is in Euclidean space, so this is just inside Rk where the variables are, well, actually d du1 up to d duk. Okay, so there's the basis vectors. Okay, so now you just need to evaluate this k form on this k tuple of tangent vectors. Okay, and you do that at each point. And that's quite easy to do. And this is where we really use the fact that this is multilinear and alternating. So let's use them one at a time. So remember, it's linear in each of the variables. Okay, so that means that you can break this up. So here you have a sum of k terms, so that breaks it up to the sum of k things. And the next one is another sum of k terms, and so forth. Okay, so you can multiply that out, and that gets you lots of terms, right? But the funny thing is that, well, here, remember, you're working in k-dimensional space, right? And so, actually, a lot of the time, you'll get repeats of these tangent vectors, these basic tangent vectors. Okay, and when you have a repeat, that gives you the value 0. So the only terms that you get is when you pick one from each of them, such that the corresponding tangent basis tangent vector is different. In other words, you have a permutation of ddu1 up to dduk. Okay, so that's the only time that works. Okay, so what are the terms that you get? Basically, you only get one term for each permutation sigma inside SK, the symmetric group on K symbols SK. Okay, and what that term will be is, well, when you look at the corresponding things, so remember, how does that work? So the value of this on d du1 up to d duk is just 1. So that means what you get is, when you evaluate this at the coefficient of d du sigma 1 up to d du sigma k, is you pull out those coefficients and you get this product of derivatives here. Okay, and what's nice is hopefully you can recognize straight away what is this term here. This term here is just the Jacobian of phi. Okay, so it turns out that this very nicely, okay, when you use this setup, it picks up the Jacobian of phi this way. And it's related to the fact that when you have the top dimensional wedge product, that's spanned by the determinant. Okay, so that's something that we see and we've used here. Okay, so that G is this. Okay, so we've computed both these two K forms, and so now we can check equality here. Okay, so what's on this side here? So this sigma upper star omega, we just wrote as this f du1 up to duk. So basically here we just have the integral of f, and that's in the u space. It's the other side, when we pull this back by phi, so we do phi upper star of this, that becomes more interesting. And what was the answer there? If we pulled that back by phi, we got this g times dt1 up to wedge up to dtk. And this g was just this term here. So now the integral that we perform is the integral over the dt, you're working in t space. Okay, it's the integral of this. So the integrand here is f composed with phi times the Jacobian here, dt1 up to dtk. And remember here, this is always positive as well because we assumed it was orientation preserving. And the thing is that, so the independence of parameterization is just equivalent to this fact here. And of course, hopefully you can recognize straight away, what is this fact? Okay, this fact is just the usual change of variables formula for integration when you integrate in Euclidean space. So the independence of parameterization is just precisely this little fact here. And in fact, the way to think about it is the way we define differential forms is to make use of this fact so that formulas like this always hold. That's how we define the differential forms, so that this would happen. And that's why we have independence of parameterization. And that gives us a very nice theory of integration on manifolds. I hope you enjoyed this adventure in pure mathematics.